Welcome to this UniLogic tutorial. UniLogic is the complete application development environment for Unitronics UniStream control platform. My name is Alex, and today's tutorial is about the FIFO and LIFO data tables. This tutorial will cover general data table requirements, an overview of how FIFO and LIFO data tables operate, ladder logic function blocks, which include push, pop, front, back, clear, and top, struct tags unique to both FIFO and LIFO tables, as well as reviewing a demonstration program for each table. When using any data table, the information is not retained by default when power is cycled. If this is required, there is 256 kilobytes of memory for retained space for both data tables and tags, since they share the same space. For additional memory, a microSD card can be utilized to store table information. Data tables are also struct-based. This tutorial will cover specific cases of using a FIFO and LIFO table. A more general explanation of setting up a data table with structs can be found in the index data table tutorial. The difference between an index table and a FIFO and LIFO table is how the information is written to each table. Instead of writing to a specific row index, both FIFO and LIFO systems use a push function to write information. They also use a pop function to remove information from the table. Each system writes, reads, and removes rows in a certain way. Using the FIFO system, which stands for first in, first out, the push command writes new information to the back or bottom of a data table. All of these rows are then shifted up by one as long as there is space. This is shown in the diagram on the page. When the push operation is performed, the information here has space in the back row, and the word Saturn is written to the back row of the table. The push command can only function if the table is not full. When full, you can use the pop function, which deletes the information in the front or top row. Here we can see a table with 5 rows that is full. When the pop operation is performed, this top row comes out of the table, and then all the rows shift upwards, leaving a row clear at the bottom. Performing a pop, then a push function will cause the information that was written to the data table first to also be the first to leave the table. Only the information in the front and back rows of the table can be read. When performing a front operation, the information in the front or top of the table will be read out. So in this instance, when the front is performed for this table, the word Venus will be read. This is also the oldest information within the table, since information is written from the back and shifted up towards the front of the table. Also is the back function. When this operation is performed, information in the back or bottom row of the table will be read. Shown here is the word Saturn. This would be the newest information since it was most recently written to the bottom of the table. Next is the LIFO system. The LIFO system stands for last in, first out, where new information is written to the front of the data table using the push function. All of the rows then are shifted down by 1. So we can see here in the LIFO system, we have a table with information in the top 4 rows, and the bottom row is empty. When the push operation is performed with the word sol, it is written to the top row of the table, and all the other rows shift down. The pop function removes the front row from the table, and the remaining rows shift up. Here, a table is full. The pop operation is performed. The topmost row is removed from the table, and all the other rows are shifted upwards. Only the top row or front row of the LIFO table can be read from the table using the top function. Using the top function here, when this is performed within the logic, it will read only the topmost row, So here it reads the newest content since it was most recently entered using a push function, and it would return the word Mercury. To better demonstrate these systems working, I have an example program for each one. First loaded will be a FIFO example. This first program uses a FIFO data table. To create this table, we will first need to create a struct. First, navigate to Structs in the Global Tag window. A struct has already been set up for this table, named Table1 Struct. We can view the tags inside by selecting the struct type. What were created were two tags for different numbers, numbers 1 and number 2, and tags for a timestamp using the real-time clock, which include the minute, hour, and second, as well as day and month of the year. After the struct was set up for the data table, we can then select the table using the same struct format. We can do this under Data Tables within the Solution Explorer on the left. We can see that this table has already been set up, and we can select it to configure the properties. The Properties window on the right allows the table to be configured. The name has already been assigned, but can be changed if necessary. The data table's type has also been selected as FIFO. LIFO and data table index are also other options. The information will not be retained. This table has been assigned 10 rows, and importantly, the struct has been selected, which defines the column structure. This was the Table1 struct, shown from the struct window below. Once this is assigned, it will show a preview of the table in the area on the left. Columns can then be modified and changed as required. Also important are tags that are automatically created within the Table1 global struct. These can be viewed in the global tag window under the table's name. Navigating to the global tag window, you see here we have our Table1 set up as a FIFO. Selecting the type, we can see the different tags that were created. These tags display the number of rows within a table, the number of occupied rows, a status, and bits for when the table is either full or empty. Though not necessary, these tags can be helpful depending upon the type of application that is being developed. After the table is set up, global structs can then be created, which will be used in the logic to write and read information. We can then view this again in the global tag window. Here there are 3 structs which are set up using the Table1 struct format. One struct for the data table information to write, and the other 2 which will contain information for the read functions from both the front and back of the data table. Next, we can navigate in the logic to see how this program will operate. Now that these structs are set up, it enables us to write information and read information from our data table. If we navigate in the ladder toolbox to Data Table FIFO, it lists all the available options, including push, pop, front, back, and clear. First, we can cover push. This is in Net 3. The push function will write information to the back row of the FIFO table and shift all other rows upwards. All you need to do is place the push block within the net, and there are only 2 input blocks for this function. The first, A, this is the selection for which data table you are writing to, we are writing to table 1. The next input is the struct source containing the information we wish to write. This will be the data to write struct. This information is constantly being generated in the first 2 nets and stored in the data to write struct. As we can see, the first 2 nets here. Every 100 milliseconds, we're adding a value to our first number here, our number 1, data to write, as well as adding another value to our second value, number 2, also in data to write. We are constantly storing the real-time clock information into the specific tags in our data to write struct for the hour, minute, second, month, and day of the year. So when the push function is performed, it takes all that information that was contained in that struct and writes it to the table. The next function is pop. This will delete the information in the front row of a FIFO table. There's only one input for this function. This is the selection for which table will perform the pop function. This is also a selection for table 1. When performed, this will delete the row information in the very top of the table. Next is clearing a table. You only need to select the clear FIFO function block and select which table to clear. In this instance, we will be clearing table 1. And also in this example, attached to this function block, I also stored 0 into all the front and back struct tags. This will be explained next. To read the information, we use the front FIFO and back FIFO function blocks. Unlike an index table, only the front and back row information can be read from the table using the FIFO system. Each function will read the front and back row of a table respectively. They each have only one input and one output. The input is which data table you're reading from. They are both reading from table number 1. The next is the output. This is the source struct that the row information will be written to. The structs that were created shown earlier in the global tag window for front FIFO and back FIFO are the structs that are going to be written. So for the front FIFO function block, we're taking information from table 1 and storing it in the struct that we called front FIFO. And when the back FIFO operation is performed, we're taking information from table 1 in the back and storing it to the FIFO back struct. This information will consistently be contained within these structs unless cleared out. This is why this example above stores 0 into the front and back struct tags. Otherwise, all the information within these structs would not be cleared, even when the data table itself has been cleared. Though not required, this example did this to visually show that no data was remaining in the table. Next, we can navigate to the HMI to see how it was set up. There's information for the data to log. This is the data to write that was referenced in the push function. You see this over here. These are the real-time clock hours, month, data to write number 1, and then data to write number 2. Also, this example's HMI does use some of the tags to display the rows used. Here we see the number of occupied rows, as well as the number of total rows. Also used are the specific bits for when the table is empty and when the table is full to light up a light on the screen. The rest of the HMI displays the real-time data being generated at the top, as well as the push, pop, and clear buttons, which trigger the functions within the logic. And to the right, the information contained in the front and back FIFO structs are also displayed. This includes the real-time clock information that was stored at the time from the front and back FIFO system. Please note that a FIFO table cannot be fully displayed on an HMI like an index table. This is due to the way a FIFO table functions. The information from the front and back of the table can be called as necessary within the program. Next, we can connect to a UniStream that already has this project loaded with the VNC viewer to better illustrate how this FIFO example works. As we can see, starting off, there are 0 rows used out of 10. The data is constantly being generated within this table. Pressing push will store this information into the first row. When I press push, we can see the used rows increments to 1. This stores the information into the back of the data table. Since there is only one row currently, both the front and back of the table display the same information. And now after the first row is written, we can see the number of occupied rows start to increment if we press the push function a couple of extra times. Each time we press the push operation, information will be written to the back of the table, and each additional row will be shifted up. We can then fill this table with information. After the table reaches the 10th row, the data table's full bit will go high. You see this down here. Pressing pop will then manually remove the frontmost row. So we see here, front FIFO. Pressing pop will then remove that row. That information will be shifted upwards. We can then press push again to fill the table. When the table is full and push is pressed, new information cannot be written. A pop function will have to be performed first. So if I try to push more information into it, see it's going to be around 40, 41, 42. Information cannot be stored into the back of the table where it's been stored previously. I would have to perform a pop operation first. That will clear out the frontmost row. There's only 9 used rows out of 10. So now when I press it, around 1720, we now see that that information was written to the back of the table. We can then clear the table. As we saw in the logic, this clears the table as well as clearing the tags within the front and back FIFO structs. This is the end of the FIFO example program. Next, I will load the LIFO program, which works similarly. Like the first example, this program writes information to a data table, with this example using HMI keypad entry to generate the data. The LIFO example has a struct that was created for the data table. We can see this under the structs tag window with the name LIFO table. We can then click on the struct type to see the individual tags that were created. There is a bit, an integer, and a real tag that have been created for this example. This struct can then be assigned to a data table. We can see this by navigating to the data tables in the Solution Explorer. We can see this table has already been created with the name LIFO test. The columns of this table are already set up according to the struct. We can use the Properties window on the right to edit this table. It has been assigned a name of LIFO test. The data table type is selected as LIFO. The table has been selected as retained. It has been assigned 10 rows, and importantly, it has been assigned the struct LIFO table, shown in the structs tag window. When created, this table is also assigned a global struct. This is shown in the global tags window. We can see it under the table's name, LIFO test, and we can select the table's type to view the different operands. Here we can see this includes the number of rows, the number of occupied rows, a status, and a bit for when the table is either full or empty. The difference between this table and the FIFO table is that information will always be written to the front row of the LIFO table and all the other rows are shifted down. This is a stack system where once all 10 rows are written, no more information can be entered. Information will have to be removed, starting with the most recent entry. We can see how this is set up within the ladder logic. Within the logic, we can see the different commands that the LIFO system uses in the toolbox under data table LIFO. The LIFO function blocks are more limited than the FIFO, with only a push, pop, top, and clear function able to be utilized. We can go over these functions now and how they work. First off, number 2 here is the push function block. This writes information to the front row of the data table. Each time this is performed, the rows shift down, and once the table is full, no more information can be written. There are 2 different inputs for this function. A, this is the data table that the information is being sent to. We will be writing information to the LIFO test table. And B, this is the struct source that contains the tag information we wish to write. This will be shown later in the HMI where we can enter the information. Next, in net 3, is the pop function. This deletes the frontmost row in the data table. All of the rows are then shifted upwards, and there's only one input for this function. That is which data table will have this pop function performed. This again will be the LIFO test data table. Next is the top function. This is the only way to read information from the specific data table. This reads the information from the front row of the table only. There is both an input and an output for this function. The input A, this is the data table that the top row is being read from. We're going to be reading from the LIFO test table. And we're going to output it to be, this is the struct source that the information will be written to. We've created a struct called top LIFO using the exact same struct we saw within the struct tag window, LIFO table, which contained the same 3 different tags. There's also a clear function here located in net number 1. Just like the FIFO system, this erases the entire data table. And again, the only thing this function requires as an input is the desired table to be cleared. In this instance, we'd be clearing the LIFO test